Audiobook Science Class 8 Page 127 Chapter 11 Forces and Pressure. In Class 7, you have learnt how objects move. Do you recall how we can decide whether an object is moving faster than the other? What does the distance moved by an object in unit time indicate? You also know that a moving object, like a ball rolling on the ground, slows down. Sometimes it may change its direction of motion. It is also possible that the ball may slow down and also change its direction. Have you ever wondered what makes an object slow down or go faster or change its direction of motion? Let us recall some of our everyday experiences. What do you do to make a football move? What do you do to make a moving ball move faster? How does a goalkeeper stop a ball? A hockey player changes the direction of the moving ball with a flick of the stick. How do fielders stop a ball hit by a batsman? As shown in figure 11.1. In all these situations, the ball is either made to move faster or slower, or its direction of motion is changed. We often say that a force has been applied on a ball when it is kicked, pushed, thrown, or flicked. What is a force? What can it do to bodies on which it is applied? We shall seek answers to such questions in this chapter. 11.1 Force. A push or a pull. Actions like picking, opening, shutting, kicking, hitting, lifting, flicking, pushing, pulling are often used to describe certain tasks. Each of these actions usually results in some kind of change in the state of motion of an object. Can these terms be replaced with one or more terms? Let us find out. Figure 11.1. A. A goalkeeper saving a goal. B. A hockey player flicking a ball. And C. A fielder stopping a ball. Option. Figure 11.1 has three images. In image A, we can see a goalkeeper saving a goal. In image B, we can see a hockey player flicking a ball. And in figure C, a fielder is shown stopping a ball. Page 128. Activity 11.1. Table 11.1 gives some examples of familiar situations involving motion of objects. You can add more such situations or replace those given here. Try to identify action involved in each case as a push and or a pull and record your observations. One example has been given to help you. Table 11.1. Identifying actions as push or pull. The table has four main columns. The first one being for serial number, second for description of the situation, third is to describe the action, which could be either pushing, pulling, picking, hitting, lifting, lowering, flying, kicking, throwing, shutting, or flicking. The fourth is action can be grouped as subcolumn 1, push, subcolumn 2, pull. Now, serial number 1, description of the situation, moving a book placed on a table. Action, pushing, pulling, lifting. Action can be grouped as a push, yes, pull, yes. Now, serial number 2, description of the situation, opening or shutting a door. 3, drawing a bucket of water from a well. 4, a football player taking a penalty kick. 5, a cricket ball hit by a batsman. 6, moving a loaded cart. 7, opening a drawer. Now make this table as just described. We have done one example for you. Now complete the table in your notebook. Do you notice that each of the actions can be grouped as a pull or a push or both? Can we infer from this that to move an object, it has to be pushed or pulled? In science, a push or a pull on an object is called a force. Thus, we can say that the motion imparted to objects was due to the action of a force. When does a force come into play? Let's find out. Paheli has an interesting question. I learnt in class 6 that a magnet attracts a piece of iron towards it. Is attraction also a pull? What about a repulsion between similar poles of two magnets? Is it a pull or a push? Page 129. 11.2. Forces are due to an interaction. Suppose a man is standing behind a stationary car, as shown in figure 11.2a. Will the car move due to his presence? Suppose the man now begins to push the car, as shown in figure 11.2b. That is, he applies a force on it. The car may begin to move in the direction of the applied force. Figure 11.2a. In figure 11.2a, we can see that a man is standing behind a stationary car. Figure 11.2b. In figure 11.2b, we can see that a car is being pushed by a man from behind. Note that the man has to push the car to make it move. Figure 11.3a. Who is pushing whom? Can you tell? In this image, who is pushing whom? Figure 11.3 shows three situations that may be familiar to you. Can you decide who is pulling and who is pushing in these cases? In figure 11.3a, both the girls appear to push each other, while the pair of girls in figure 11.3b are trying to pull each other. Figure 11.3b. Who is pulling whom? Similarly, the cow and the man in figure 11.3c appear to pull each other. Figure 11.3c. Who is pulling whom? Now, check figure 11.3c. Can you tell who is pulling whom? Is the man pulling the cow or the cow pulling the man? The girls in the two situations, figure 11.3a and 11.3b, are applying force on each other. Is it also true for the man and the cow? From these examples, we can infer that at least two objects must interact for a force to come into play. Thus, an interaction of one object with another object results in a force between the two objects. Page 130. 11.3. Exploring forces. Let us try to learn more about forces. Activity 11.2. Choose a heavy object like a table or a box, which you can move only by pushing hard. Try to push it all by yourself. Can you move it? Now, ask one of your friends to help you in pushing it in the same direction as shown in figure 11.4a. Is it easier to move it now? Can you explain why? Now, push the same object, but ask your friend to push it from the opposite side, as shown in figure 11.4b. Does the object move? If it does, note the direction in which it moves. Can you guess which one of you is applying a larger force? Figure 11.4. Two friends pushing a heavy load. A in the same direction, B in the opposite direction. Have you ever seen a game of tug of war? In this game, two teams pull at a rope in opposite directions, as shown in figure 11.5. Members of both the teams try to pull the rope in their direction. Figure 11.5. The rope may not move if the two teams pull at it with equal force. Option. In figure 11.5, you can see that the rope is not moving anywhere because the two teams are pulling it with equal force. Sometimes the rope simply does not move. Is it not similar to the situation shown in figure 11.3b? The team that pulls harder, that is, applies a large force, finally wins the game. What do these examples suggest about the nature of force? Forces applied on an object in the same direction add to one another. Now, recall what happened when you and your friend pushed the heavy box in the same direction as shown in activity 11.2. If the two forces act in the opposite directions on an object, the net force acting on it is the difference between the two forces. What did you observe in activity 11.2 when both of you were pushing the heavy box from opposite directions? Recall that in the tug of war, when two teams pull equally hard, the rope does not move in any direction. So, we learned that a force could be larger or smaller than the other or equal to each other. The strength of a force is usually expressed by its magnitude. We have also to specify the direction in which a force acts. Also, if the direction or the magnitude of the applied force changes, its effect also changes. Paheli asks, does it mean that the net force on an object is zero if the two forces acting on it in opposite directions are equal? Page 131. In general, more than one force may be acting on an object. However, the effect on the object is due to the net force acting on it. 11.4. A force can change the state of motion. Let us find out what happens when a force acts on an object. Activity 11.3. Take a rubber ball and place it on a level surface such as a tabletop or a concrete floor. Now, gently push the ball along the level surface as shown in figure 11.6. Does the ball begin to move? Push the ball again while it is still moving. Is there any change in its speed? Does it increase or decrease? Next, place your palm in front of the moving ball. Remove your palm as soon as the moving ball touches it. Does your palm apply a force on the ball? What happens to the speed of the ball now? Does it increase or decrease? What would happen if you let your palm hold the moving ball? In figure 11.6, that the ball starts moving as soon as a force is applied on it. You might recall similar situations. For example, while taking a penalty kick in football, the player applies a force on the ball. Before being hit, the ball was at rest and so its speed was zero. The applied force makes the ball move towards the goal. Suppose the goalkeeper dives or jumps up to save the goal. By his action, the goalkeeper tries to apply a force on the moving ball. The force applied by him can stop or deflect the ball, saving a goal being scored. If the goalkeeper succeeds in stopping the ball, its speed decreases to zero. These observations suggest that a force applied on an object may change its speed. If the force applied on the object is in the direction of its motion, the speed of the object increases. If the force is applied in the direction opposite to the direction of motion, then it results in a decrease in the speed of the object. Bujo says, I have seen children competing with one another in moving a rubber tire or a ring by pushing it, as shown in figure 11.7. I now understand why the speed of the tire increases whenever it is pushed. Figure 11.7. To move a tire faster, it has to be pushed repeatedly. Page 132. Paheli is curious to know whether application of a force can only change the speed of an object. Let us find out. Activity 11.4. Take a ball and place it on a level surface as you did in activity 11.3. Make the ball move by giving it a push as shown in figure 11.8a. Now, place a ruler in its path as shown in figure 11.8b. In doing so, you would apply a force on the moving ball. Does the ball continue to move in the same direction after it strikes the ruler? Repeat the activity and try to obstruct the moving ball by placing the ruler in such a way that it makes different angles to its path. In each case, note your observations about the direction of motion of the ball after it strikes the ruler. Figure 11.8a. A ball set in motion by pushing it along a level surface, and b. The direction of motion of the ball after it strikes the ruler placed in its path. Let us consider some more examples. In a game of volleyball, players often push the moving ball to their teammates to make a winning move. Sometimes the ball is returned to the other side of the court by pushing or smashing it. In cricket, a batsman plays his or her shot by applying a force on the ball with the bat. Is there any change in the direction of motion of the ball in these cases? In all these examples, the speed and the direction of the moving ball change due to the application of a force. Can you give a few more examples of this kind? A change in either the speed of an object or its direction of motion, or both, is described as a change in its state of motion. Thus, a force may bring a change in the state of motion of an object. State of motion. The state of motion of an object is described by its speed and the direction of motion. The state of rest is considered to be the state of zero speed. An object may be at rest or in motion, both are its states of motion. Does it mean that the application of a force would always result in a change in the state of motion of the object? Let us find out. It is common experience that many a time application of force does not result in a change in the state of motion. For example, a heavy box may not move at all, even if you apply the maximum force that you can exert. Again, no effect of force is observed when you try to push a wall. Page 133. 11.5. Force can change the shape of an object. Activity 11.5. Some situations have been given in column 1 of table 11.2 in which objects are not free to move. Column 2 of the table suggests the manner in which a force can be applied on each object, while column 3 shows a diagram of the action. Try to observe the effect of force in as many situations as possible. You can also add similar situations using available material from your environment. Note your observations in column 4 and 5 of the table. Table 11.2. Studying the effect of force on objects. The table has 4 columns. First one being description of situation, second, how to apply force, third, diagram, and fourth, action of force. And it has 2 subcolumns, change in state of motion and change in shape. Under that, you have to give answers yes, no, yes, no. The first situation is a lump of dough on a plate. How to apply force? Pressing it down with your hands. Diagram. In the image, we can see pressure being applied by hands on lump of dough. Now in the fourth column, action of force, change in state of motion or change in shape. You have to give the correct answer. Second situation, spring fixed to the seat of a bicycle. How to apply force? By sitting on the seat. Diagram, we can see an image where a person is sitting on the seat of a bicycle. Now in the next column of action of force, you have to give the correct answer. Third situation, a rubber band suspended from a hook or a nail fixed on a wall. How to apply force? By hanging a weight or by pulling its free end. Diagram, the image shows it clearly. Now you have to give the correct answer in the column of action of force. Next situation, a plastic or metal scale placed between 2 bricks. How to apply force? By putting a weight at the center of the scale. Diagram, the image shows the action clearly. Now, action of force, you have to give correct answer in this column. Page 134. What do you conclude from the observations noted in table 11.2? What happens when you apply a force on an inflated balloon by pressing it between your palms? What happens to the shape of a ball of dough when it is rolled to make a chapati? What happens when you press a rubber ball placed on a table? In all these examples, you saw that the application of force on an object may change its shape. Having performed all the above activities, you would have realized that a force, number 1, may make an object move from rest. Number 2, may change the speed of an object if it is moving. Number 3, may change the direction of motion of an object. Number 4, may bring about a change in the shape of an object. Number 5, may cause some or all of these effects. While a force may cause one or more of these effects, it is important to remember that none of these actions can take place without the action of a force. Thus, an object cannot move by itself. It cannot change speed by itself. It cannot change direction by itself. And its shape cannot change by itself. 11.6. Contact forces. Muscular force. Can you push or lift a book lying on a table without touching it? Can you lift a bucket of water without holding it? Generally, to apply a force on an object, your body has to be in contact with the object. The contact may also be with the help of a stick or a piece of rope. When we push an object like a school bag or lift a bucket of water, where does the force come from? This force is caused by the action of muscles in our body. The force resulting due to the action of muscles is known as the muscular force. It is the muscular force that enables us to perform all activities involving movement or bending of our body. In class 7, you have learnt that in the process of digestion, the food gets pushed through the alimentary canal. Could it be a muscular force that does it? You also know that lungs expand and contract while we inhale and exhale air during breathing. Where are these muscles located, which make breathing possible? Can you list a few more examples of the force exerted by the muscles in our body? Animals also make use of muscular force to carry out their physical activities and other tasks. Animals like bullocks, horses, donkeys, and camels are used to perform various tasks for us. In performing these tasks, they use muscular force, as shown in figure 11.9. Figure 11.9. Muscular force of animals is used to carry out many difficult tasks. Here, the muscular force of animals is in force. Page 135. Since muscular force can be applied only when it is in contact with an object, it is also called a contact force. Are there other types of contact forces? Let us find out. Friction. Recall some of your experiences. A ball rolling along the ground gradually slows down and finally comes to rest. When we stop pedaling a bicycle, it gradually slows down and finally comes to a stop. A car or a scooter also comes to rest once its engine is switched off. Similarly, a boat comes to rest if we stop rowing it. Can you add some more such experiences? In all these situations, no force appears to be acting on the objects, yet their speed gradually decreases and they come to rest after some time. What causes a change in their state of motion? Could some force be acting on them? Can you guess the direction in which the force must be acting in each case? The force responsible for changing the state of motion of objects in all these examples is the force of friction. It is the force of friction between the surface of the ball and the ground that brings the moving ball to rest. Similarly, friction between water and the boat brings it to a stop once you stop rowing. The force of friction always acts on all the moving objects and its direction is always opposite to the direction of motion. Since the force of friction arises due to contact between surfaces, it is also an example of a contact force. You will learn more about this force in chapter number 12. You may be wondering whether it is essential for the agent applying a force on an object to be always in contact with it. Let us find out. 11.7. Non-contact forces. Magnetic force. Activity 11.6. Take a pair of bar magnets. Place the longest side of one of the magnets over 3 round-shaped pencils or wooden rollers as shown in figure 11.10. Now, bring one end of the other magnet near the end of the magnet placed on the rollers. Make sure that the two magnets do not touch each other. Observe what happens. Next, bring the other end of the magnet near the same end of the magnet placed on the rollers as shown in figure 11.10. Note what happens to the magnet placed on the rollers every time another magnet is brought near it. Figure 11.10. In figure 11.10, we can see attraction and repulsion between two magnets. Page 136. Does the magnet on the rollers begin to move when the other magnet is brought near it? Does it always move in the direction of the approaching magnet? What do these observations suggest? Does it mean that some force must be acting between the two magnets? You have learnt in class 6 that like poles of two magnets repel each other and unlike poles attract each other. Attraction or repulsion between objects can also be seen as another form of pull or push. Do you have to bring the magnets in contact for observing the force between them? A magnet can exert a force on another magnet without being in contact with it. The force exerted by a magnet is an example of a non-contact force. Similarly, the force exerted by a magnet on a piece of iron is also a non-contact force. Electrostatic force. Activity 11.7. Take a plastic straw and cut it into nearly 2 equal pieces. Suspend one of the pieces from the edge of a table with the help of a piece of thread, as shown in figure 11.11. Now, hold the other piece of straw in your hand and rub its free end with a sheet of paper. Bring the rubber end of the straw near the suspended straw. Make sure that the two pieces do not touch each other. What do you observe? Next, rub the free end of the suspended piece of straw with a sheet of paper. Again, bring the piece of straw that was rubbed earlier with paper near the free end of the suspended straw. What do you observe now? Figure 11.11 helps us to understand that when a straw rubbed with paper, it attracts another straw, but repels it if it has also been rubbed with a sheet of paper. A straw is said to have acquired electrostatic charge after it has been rubbed with a sheet of paper. Such a straw is an example of a charged body. The force exerted by a charged body on another charged or uncharged body is known as electrostatic force. This force comes into play even when the bodies are not in contact. The electrostatic force, therefore, is another example of a non-contact force. You will learn more about electric charges in chapter 15. Gravitational forces. You know that a coin or a pen falls to the ground when it slips off your hand? Leaves and fruits also fall to the ground when they get detached from the plant. Have you ever wondered why it is so? When the coin is held in your hand, it is at rest. As soon as it is released, it begins to move downwards. It is clear that the state of motion of the coin undergoes a change. Can this happen without a force acting on it? Which is this force? Page 137. Objects or things fall towards the earth because it pulls them. This force is called the force of gravity, or just gravity. This is an attractive force. The force of gravity acts on all objects. The force of gravity acts on all of us all the time without our being aware of it. Water begins to flow towards the ground as soon as we open a tap. Water in rivers flows downward due to the force of gravity. Gravity is not a property of the earth alone. In fact, every object in the universe, whether small or large, exerts a force on every other object. This force is known as the gravitational force. 11.8. Pressure. You have learnt in class 7 that strong winds during a storm or a cyclone can blow away even the rooftops. You also learnt that winds and cyclones are caused by the differences in air pressure. Is there any relation between pressure and force? Let us find out. Try to push a nail into a wooden plank by its head. Did you succeed? Try now to push the nail by the pointed end, as shown in figure 11.12. Could you do it this time? Figure 11.12. Pushing a nail into a wooden plank. Try cutting vegetables with a blunt knife and then with a sharp knife. Which is easier? Do you get the feeling that the area over which the force is applied, for example, the pointed end of the nail, plays a role in making these tasks easier? The force acting on a unit area of a surface is called pressure. Pressure is equal to force by area on which it acts. At this stage, we consider only those forces which act perpendicular to the surface on which the pressure is to be computed. Paheli said, I now understand why porters place a round piece of cloth on their heads when they have to carry heavy loads, as shown in figure 11.13. By doing this, they increase the area of contact of the load with their head. So, the pressure on their head is reduced and they find it easier to carry the load. Figure 11.13. A porter carrying a heavy load. Page 138. Note that the area is in the denominator in the above expression. So, the smaller the area, larger the pressure on a surface for the same force. The area of the pointed end of the nail is much smaller than of its head. The same force, therefore, produces a pressure sufficient to push the pointed end of the nail into the wooden plank. Can you explain now why shoulder bags are provided with broad straps and not thin strap? And why the tools meant for cutting and piercing always have sharp edges? Do liquids and gases also exert pressure? Does it also depend on the area on which the force acts? Let us find out. 11.9. Pressure exerted by liquids and gases. Activity 11.8. Take a transparent glass tube or a plastic pipe. The length of the pipe or tube should be about 25 centimeter and its diameter should be 5 to 7.5 centimeter. Also, take a piece of thin sheet of a good quality rubber, say a rubber balloon. Stretch the rubber sheet tightly over one end of the pipe. Hold the pipe at the middle, keeping it in a vertical position, as shown in figure 11.14. Ask one of your friends to pour some water in the pipe. Does the rubber sheet bulge out? Note also the height of the water column in the pipe. Pour some more water. Observe again the bulge in the rubber sheet and the height of the water column in the pipe. Repeat this process a few more times. Can you see any relation between the amount of the bulge in the rubber sheet and the height of the water column in the pipe? Figure 11.14 proves that pressure exerted by water at the bottom of the container depends on the height of its column. Activity 11.9. Take a plastic bottle. You can take a discarded water or soft drink bottle. Fix a cylindrical glass tube, a few centimeters long near its bottom as shown in figure 11.15. You can do so by slightly heating one end of the glass tube and then quickly inserting it near the bottom of the bottle. Make sure that the water does not leak from the joint. If there is any leakage, seal it with molten wax. Cover the mouth of the glass tube with a thin rubber sheet as you did in activity 11.8. Now fill the bottle up to half with water. What do you observe? Why does the rubber sheet fixed to the glass tube bulge this time? Page 139. Pour some more water in the bottle. Is there any change in the bulge of the rubber sheet? Figure 11.15. In the image shown in figure 11.15, we can clearly see that liquid exerts pressure on the walls of the container. Note that the rubber sheet has been fixed on the side of the container and not at the bottom. Does the bulging of the rubber sheet in this case indicate that water exerts pressure on the sides of the container as well? Let us investigate further. Activity 11.10. Take an empty plastic bottle or a cylindrical container. You can take a used tin can or a used plastic bottle. Drill 4 holes all around near the bottom of the bottle. Make sure that the holes are at the same height from the bottom as shown in figure 11.16. Now fill the bottle with water. What do you observe? Do the different streams of water coming out of the holes fall at the same distance from the bottle? What does this indicate? Figure 11.16. Figure 11.16 demonstrates that liquids exert equal pressure at the same depth. Can you now say that liquids exert pressure on the walls of the container? Do gases also exert pressure? Do they also exert pressure on the walls of their containers? Let us find out. Bujo happily says, I have seen fountains of water coming out of the leaking joints or holes in pipes supplying water. Is it not due to the pressure exerted by water on the walls of the pipes? When you inflate a balloon, why do you have to close its mouth? What happens when you open the mouth of an inflated balloon? Suppose you have a balloon which has holes. Would you be able to inflate it? If not, why? Can we say that air exerts pressure in all directions? Page 140. Do you recall what happens to the air in the bicycle tube when it has a puncture? Do these observations suggest that air exerts pressure on the inner walls of an inflated balloon or a tube? So, we find that gases too exert pressure on the walls of their container. 11.10. Atmospheric pressure. You know that there is air all around us. This envelope of air is known as the atmosphere. The atmospheric air extends up to many kilometers above the surface of the earth. The pressure exerted by this air is known as atmospheric pressure. We know that pressure is force per unit area. If we imagine a unit area and a very long cylinder standing on it filled with air, then the force of gravity on the air in the cylinder is the atmospheric pressure, as shown in figure 11.17. Figure 11.17. Figure 11.17 demonstrates that atmospheric pressure is the force of gravity on air in a column of unit area. But how large or small is the atmospheric pressure? Let us get an idea about its magnitude. Activity 11.11. Take a good quality rubber sucker. It looks like a small rubber cup, as shown in figure 11.18. Press it hard on a smooth plain surface. Does it stick to the surface? Now try to pull it off the surface. Can you do it? Figure 11.18 shows a rubber sucker pressed on a surface. When you press the sucker, most of the air between its cup and the surface escapes out. The sucker sticks to the surface because the pressure of atmosphere acts on it. To pull the sucker off the surface, the applied force should be large enough to overcome the atmospheric pressure. This activity might give you an idea about the magnitude of atmospheric pressure. In fact, it would not be possible for any human being to pull the sucker off the surface if there were no air at all between the sucker and the surface. Does it give you an idea how large the atmospheric pressure is? Page 141. Bujo wonders, if the area on my head were 15 centimeter by 15 centimeter, how much force air will exert on my head? The force due to air in a column of the height of the atmosphere and area 15 centimeter by 15 centimeter, as shown in figure 11.19, is nearly equal to the force of gravity on an object of mass 225 kg, 2250 N. The reason we are not crushed under this force of gravity is that the pressure inside our bodies is also equal to the atmospheric pressure and balances the pressure from outside. Figure 11.19. Pressure of atmosphere on your head. Did you know Otto von Guericke, a German scientist of the 17th century, invented a pump to extract air out of a vessel? With the help of this pump, he demonstrated dramatically the force of the air pressure. He joined two hollow metallic hemispheres of 51 centimeter diameter each and pumped air out of them. Then he employed 8 horses on each hemisphere to pull them apart, as shown in figure 11.20. So great is the force of air pressure that the hemispheres could not be pulled apart. Figure 11.20. Horses pulling the hemispheres. Page 142. Keywords: atmospheric pressure, contact force, electrostatic force, force, friction, gravitational force, gravity, magnetic force, muscular force, non-contact force, pressure, pull, push. What you have learnt. Force could be a push or a pull. A force arises due to the interaction between two objects. Force has magnitude as well as direction. A change in the speed of an object or the direction of its motion or both implies a change in its state of motion. Force acting on an object may cause a change in its state of motion or a change in its shape. A force can act on an object with or without being in contact with it. Force per unit area is called pressure. Liquids and gases exert pressure on the walls of their containers. The pressure exerted by air around us is known as atmospheric pressure. Exercises. 1. Give 2 examples each of situations in which you push or pull to change the state of motion of objects. 2. Give 2 examples of situation in which applied force causes a change in the shape of an object. 3. Fill in the blanks in the following statements. A. To draw water from a well, we have to blank at the rope. B. A charged body, blank an uncharged body towards it. C. To move a loaded trolley, we have to blank it. D. The north pole of a magnet, blank the north pole of another magnet. Page 143. 4. An archer stretches her bow while taking aim at the target. She then releases the arrow, which begins to move towards the target. Based on this information, fill up the gaps in the following statements using the following terms. The terms are muscular, contact, non-contact, gravity, friction, shape, attraction. A. To stretch the bow, the archer applies a force that causes a change in its blank. B. The force applied by the archer to stretch the bow is an example of blank force. C. The type of force responsible for a change in the state of motion of the arrow is an example of a blank force. D. While the arrow moves towards its target, the forces acting on it are due to blank and that due to blank of air. 5. In the following situations, identify the agent exerting the force and the object on which it acts. State the effect of the force in each case. A. Squeezing a piece of lemon between the fingers to extract its juice. B. Taking out paste from a toothpaste tube. C. A load suspended from a spring while its other end is on a hook fixed to a wall. D. An athlete making a high jump to clear the bar at a certain height. 6. A blacksmith hammers a hot piece of iron while making a tool. How does the force due to hammering affect the piece of iron? 7. An inflated balloon was pressed against a wall after it has been rubbed with a piece of synthetic cloth. It was found that the balloon sticks to the wall. What force might be responsible for the attraction between the balloon and the wall? 8. Name the forces acting on a plastic bucket containing water held above ground level in your hand. Discuss why the forces acting on the bucket do not bring a change in its state of motion. 9. A rocket has been fired upwards to launch a satellite in its orbit. Name the two forces acting on the rocket immediately after leaving the launching pad. 10. When we press the bulb of a dropper with its nozzle kept in water, air in the dropper is seen to escape in the form of bubbles. Once we release the pressure on the bulb, water gets filled in the dropper. The rise of water in the dropper is due to A. Pressure of water, B. Gravity of the earth, C. Shape of rubber bulb, D. Atmospheric pressure. Page 144. Extended learning. Activities and projects. 1. Make a 50 centimeter by 50 centimeter bed of dry sand about 10 centimeter in thickness. Make sure that its top surface is leveled. Take a wooden or a plastic stool. Cut 2 strips of graph paper each with a width of 1 centimeter. Paste them vertically on any leg of the stool. One at the bottom and the other from the top. Now gently put the stool on the sand bed with its legs resting on the sand. Increase the size of sand bed if required. Now put a load, say a school bag full of books, on the seat of the stool. Mark the level of sand on the graph strip. This would give you the depth, if any, to which the legs of stool sink in sand. Next, turn the stool upside down so that now it rests on its seat on the sand bed. Note the depth to which the stool sinks now. Next, put the same load on the stool and note the depth to which it sinks in the sand. Compare the pressure exerted by the stool in the two situations. 2. Take a tumbler and fill it with water. Cover the mouth of the tumbler with a thick card similar to that of a postcard. Hold the tumbler with one hand while keeping the card pressed to its mouth with your other hand. Turn the tumbler upside down while keeping the card pressed to its mouth. Make sure that the tumbler is held vertical. Gently remove the hand pressing the card. What do you observe? Does the card get detached, allowing the water to spill? With a little practice, you will find that the card continues to hold water in the tumbler even after it is not supported by your hand. Also try this activity by using a piece of cloth to hold the tumbler in an upside-down position as shown in figure 11.21. Page 145. 3. Take 4-5 plastic bottles of different shapes and sizes. Join them together with small pieces of glass or rubber tube as shown in figure 11.22. Keep this arrangement on a level surface. Now pour water in any one of the bottles. Note whether the bottle in which water is poured gets filled first or all the bottles get filled up simultaneously. Note the level of water in all the bottles from time to time. Try to explain your observations. Chapter 11 ends here.